All right, hello everyone. Happy Thursday. We are on the 10th week of classes, and this semester just flew by. All right, so we're gonna start our new lecture on chapter. We're gonna learn about non-linear programming or non-linear optimization models. That means that model is non-linear. We have kind of had a problem like that, but we're gonna dive in deeper. Okay, let's get started. Let me pull up the lecture slides. So these are available on iLearn, and download them. Right, NLP or nonlinear programming or optimization models, nonlinear models. There are many actually problems that they are not confining with our standard definition of linear function, whether the objective function has a nonlinearity kind of part into it, or whether the constraints have. And any violation of nonlinearity in the model is going to make it nonlinear. And there are a lot of problems that they have nonlinearity in them, whether in the objective function or whether the constraints. Examples you're going to see, for example, the marketing. We have kind of had an example of, if you remember, the advertising, the exposure to advertising. We assume that the revenue generation was a linear function of the ad exposure, which is kind of a big and suspicious assumption. We don't really believe that if a person sees an ad multiple times, it's going to have the same effect. It's going to have a decreasing marginal effect, right? The marginal effect is going to be decreasing, right? So that's actually a concept that is best modeled as a nonlinear function rather than a linear function. Another example is the finance. In finance, when actually risk depends on the portfolio variance, which is the nonlinear function. We're going to have an example of finance, the demand and profit, and the demand and price. Actually, we're going to see an example of that. And another example is in statistics or regressions, the least square function. If you remember from statistics or any other course where you have learned about linear regression, the least square function actually finds it's actually a nonlinear function. It's a square of the difference between the prediction and the original value, as we're going to see, as you can see here. So we are summing up the difference between the real and actual value minus our prediction is squared for any data that we have. So this is a nonlinear function. And the least square, that means we're minimizing it. So that's a good fit for an optimization model. So we're going to do an example of that. All right, so let's see an example for nonlinear programming. This is a small example just for illustration. It has only two variables, x and y. So the function is 2 multiplied by x minus 2 squared plus 1 minus 1 squared. As you see here, the two components of objective function, the first one and second one, both are nonlinear. But even just one part is enough. If we only had this part and this part was linear, it still would be nonlinear. Okay, so any violation is going to make it. The constraints are linear actually, but that doesn't help. Still, the objective function is nonlinear. So we're going to actually classify this as a nonlinear programming problem, NLP. So it's fairly simple model. So let's see how we can actually solve this. Right, the unconstrained minimum is at this is actually the minimum, x and y equal to 2 and 1. X is 1 and x is 2 and y is 1. But this is the unconstrained. That means that it's going to actually violate our constraints. But if you don't consider the constraint, the minimum you get this is when x is 2, which is this component is 0, and when y is 1, which is this component is here. Because these two values are squared, that means that they never actually are negative, right? So you are adding two non-negative values together, and the minimum for that is 0 when both values are 0. So that means that this is equal to 0, which x is equal to 2, and this equal to 0, which means y is equal to 1. But that does not consider the constraints that we have. The constraints here, it says that, for example, x plus y must be greater than or equal to 5, and 2 plus 1 is 3, which is not equal to 5. So that y is that means that this is not the feasible solution. So it's not an optimal solution for us. All right, so how we can actually do that? Let's actually go back to the graphical method approach that we had for the two variables before we started the simplex algorithm. So what we're gonna do, because we have two variables here, it's a two-dimensional problem, so we can actually graph it in a two-dimensional space, x-axis and y-axis. This is the first constraint. The first constraint is that x plus y is equal to greater than equal to 5. So this is the first constraint, greater than equal to 5. The second constraint is x should be less than 7. X is less than 7. The third constraint is y should be less than 6. Y is less than 6, and that's about it. This is our feasible region. Now, we need to find the optimal solution, and the optimal solution is going to be a feasible solution, but we don't know where it is. For linear programming, we actually had a very super helpful theorem, mathematical theorem, that it would tell us that, right, forget about anything else, only consider the extreme points. So we only have limited extreme points here, as you see, 1, 2, 3, 4, and 5. So we only have to evaluate 5 points here to see which one is actually has a higher value. I mean, actually, because we're minimizing, has a smaller value. So that would be our optimal solution. But here, because we are dealing with a nonlinear objective function, that does not work for us. So the solution, optimal solution, is not necessary in the extreme points, and we have actually infinite possibilities for that. So that's what makes it more challenging. So generally, nonlinear programming are more challenging to solve than linear programming. For example, if you plug in any of these extreme points into the objective function, you're going to see that it's not off. For example, see when x is 2 and y is 3, you get z equal to 4. When x is 5 and y is 0, x is 5, y is 0. So you get 1 here, you get 9 here, 9 multiplied by 2, 18 plus 1, 19. So you get 19 here, which is not minimum, right? Again, this is 5 and 0, 0 and 5. So 0 and 5, this is 0, that's 4, 4 multiplied by 2, 8, 8 plus 4, 16, 16. So that's not our minimum either. But as you see here, out of the loop, this point in the middle, which is not an extreme point, actually produces a smaller value than those, is equal to 4. All right, so what should we do? We're not going to go into detail and introduce like a nonlinear programming algorithm here. So we're just going to use Excel solver. So let's do that. Right. So before we go to the Excel file, suppose that we have n data points. Each one of them have its own variable dimension, which is xi. We have x and y. So we have n data points. The least square regression finds a function. This is what we want. This is the problem that we want to solve. We want to find a predictive function, linear function. That's why we show it by y hat. This is called y hat. Y hat. So it's a function of x, f of x, so that it minimizes the sum of the squared errors. And that means that we are trying to find the best fitting function for our x and y, our values here. Okay? And y, our prediction is a function of x. Okay? And this is the least square function. you're going to find the difference between the original value, yi, which we have it the data here, and our predictive value, which is going to use this function here. And then the difference between these two is going to be the error of our prediction. If they are exactly equal, that means that we have 0 errors, and that's perfect. That's a perfect actually prediction or fitness, but generally it's not. So the difference between two plus 2, we are squaring them, and then we're going to sum them up. Because why we are squaring them? Because if we don't, there is a possibility that negative and positive errors, they're going to cancel each other out. So we're going to get an average of 0, which is not true, right? So that's why we square them, to cancel the negativity possibility, to cancel out possibility of the negative and positive errors. The specific form of the regression function can be linear. So f of x can be linear, can be non-linear, such as the logarithmic, natural logarithmic, polynomial, so on and so forth. But anyhow, no matter what fx is, the least square function is actually a non-linear function because it's a square. So the problem is how to choose the best fitting parameters for any specific regression function, whether it's linear or non-linear, right? So let's try with a non-linear fx. Okay? So fx can be linear or non-linear. For example, suppose that we want to use the natural logarithm. That's ln of x, natural logarithm of x. So this is the function. We assume that we want to actually find the parameters a and b. So we assume that our prediction for y is a function of x, and that's natural logarithm of x multiplied by b, parameter b, which is kind of slope plus a. And we want to find a and b in a way that, so it's going to be our decision variable, so that the least square is minimized. Okay? So that's going to be our objective function, and our decision variable is going to be a and b parameters. All right, so we have 4 points here. These are our data, x1 and y1, x3 and y7, x5 and y8, x8 and y10. These are the points that we have plotted here in this graph. And what we are trying to find is actually the best fit natural logarithm function using this function, a plus b multiplied by natural logarithm of x. So it's going to be a curve like this. Its curve is non-linear, but we are trying to find a and b is such that it is the best fit. That means it's best prediction that these points are going to fit into. Okay? So let's go to the Excel file, and I am going to open this. This is the data file. So this is the algebraic formulation. We are minimizing, let me bring this here. So we are minimizing the least square. That's 2 multiplied by x minus 2 squared plus y minus 1 squared. That's our objective function. This is the previous problem. X plus y has to be greater than 5. X should be less than 7. Y should be less than 6. And x should be, x and y, we want it to be positive. Okay. So we're going to set up our model in Excel friendly model. So we're going to define a decision variable, x and y here. This is a decision variable. The objective function is going to be here. These are the constraints here. So that means x plus y should be greater than 5. So that's 1 multiplied by x plus 1 multiplied by y should be greater than 5. So here we're going to write the left-hand side here. That's x plus y using this kind of matrix here. So this is what I'm going to do. I'm going to say, let me actually, before we do that, let's name these decision variables here. So the objective function, that too. So now it's easier to do that. So this is going to be the sum product of the decision variables and our matrix here. So now I can drag it down. I'll make sure that. Okay, now it's working. All right, so it works. Let me try different values here, 1 and 2, for example. All right. So the left-hand side, the first one is x plus y should be greater than 5. But this is not necessary. You have to multiply this, but it is fine because this is x plus y, so it works. But anyway. This should be greater than 5, which is not. So this is not a feasible solution. This has to be less than 7, which is. This has to be less than 6, which is. So, but generally, this is not a feasible solution. And we're going to write our objective function. So the objective function should be 2 multiplied by x minus 2 squared plus y minus 1 squared. 2 multiplied by x minus 2 squared and plus y minus 1 squared. So this seems to be correct. And that's actually 1 minus 2, that's 1 squared, that's 1. 2 multiplied by 1, that's 1. And 2 minus 1 is 1, squared is 1 still. So that will be 2 plus 1, which is 3. So this is correct. All right, so what else do we have? X and y has to be greater than 0. We don't seem to have any other actually components here to do. So I'm going to name actually these two. The left-hand side and right-hand side, I'm going to name them. So now we are good to go. I'm going to go to data solver. We are minimizing the objective function. So I'm going to find the minimization. And this is our objective function. And the variables are here. And I'm going to add the constraints here. So the first constraint is x plus y should be greater than 5. That's our left-hand side should be greater than 5. So 5. I'm going to add that. The next constraint, because these two have equal, less than equal to, say they have the similar equality sign, inequality sign, I'm going to grab both of them. I'm going to say this should be less than equal to these two values. So I'm going to grab those two. All right. X and y should be non-negative, so make sure that this is checked. And from this solution method, solving method, we're gonna pick the GRG nonlinear. All right. So we're not gonna go through the options right now, maybe later. So that's about it. We are going to just click on the solve, and you see that it's going to change it. So this is what it says. Solver found a solution. It didn't say that it's optimal or not. It says actually all constraints and optimal conditions are satisfied. But actually here it says it's optimal. It says it's optimal. But not necessarily with the nonlinear programming, depending on the problem, we cannot be sure whether we have solved it optimally or not. Here, because it's a specific problem, it actually that's why it can with certainty set that it's optimal. So this is the optimal solution. And the optimal solution as x should be 2.67, y should be 2.33. And with that, we're going to get z equal to 2.67. All right. Let me go back to the slide. So as I said, generally non-linear programming, the NLPs are harder to solve. And the other thing about it is that unlike the linear programming, we are not sure whether we have the optimal solution or not. And that's a challenge. There are certain scenarios that we can be sure, but not always. And also sometimes, or most of the time with the Excel solver, the GRG solver, the initial solution that you work with, like the values that I put under X and Y, that initial value that you start the solution with, the solution approach with, that's going to impact how long it's going to run, and also your optimal, your final solution. In this scenario, because the problem is convex, so because the objective function is convex, yeah, so that means, and then because the problem is minimization problem, for the convex objective function or minimization problem, we can be sure that we have found optimal solution. But if it's not convex, then we cannot be sure. Right? So convex is like this shape. So this shape, and it's non-increasing. All right. And let's also talk about the global and local. That's one of the issues that we have with the nonlinear programming. We have, it could be optimal solution, but compared to what is called its own neighborhood, that means that considering the values close by the X and Y or other variables, that's vicinity of those values, it can be considered as an optimal, but in overall, it's not. So that's why we have the two concepts here: the local optimum and the global optimum. So the global optimum is when you have the best optimal solution, and the local is just its best compared to its own neighborhood. So let's see an example of that. So this looks a crazy function, as you see here. And this is a function: x minus 1 multiplied by x minus 2 multiplied by x minus 3 multiplied by x minus 4 multiplied by x minus 5. And this is how it looks from, from 1 to 5. This is how it looks. It has these up and downs. And as you can see here, we get a lot of actually like 1, 2, 3, 4 up and downs here. For example, this point here, compared to this one, this is the optimal minimum, because this is like 2 dimensions. So by eyeballing, it's very easy for us to find the optimal solution. This is the minimum point, right? This is also minimum, but it's local because it is like compared to the values here, these points here, this is actually minimum. But compared to this is not. So this is the global minimum, and this is the local minimum. Same goes for these 2 points. Actually, we can also consider this one, depending on the bracket that you choose for. So this is optimal, maximum, compared to these values, compared to this bracket. But globally, this is better. So this is the global optimum, this is the local optimum. And one of the issues and challenges that we have with the nonlinear solvers is that your solver can get stuck into the local optimum. So when it tries to figure out whether it has found the optimal solution, because it's in the local optimal solution, it kind of, the signals are, yes, you are in an optimal solution, but it cannot be sure whether it's an optimal global optimal or a local optimal. And that's one of the challenges too. So let me actually open up an example of when you're stuck, when you want to solve a problem, and you get stuck into local optimal. Close this exercise. All right. So this is what we have. We want to maximize f of x, which is this graph like here, x minus 1 multiplied x minus 2 multiplied by x minus 3 and x minus 4 and x minus 5. So I have given it the value to plot these points here. I have given it values from 0.9 almost 1 to almost 5 by increment of 0.1 here. So 0.9, the next one by x value is 1, 1.1, and we're going to go to up to 5.1. So we have covered this area from this point up to this point. And the fx value is just this value. It's this function for x. Okay, so this is x minus 1 multiplied by this x minus 2 multiplied by x minus 3 multiplied by x minus 4 multiplied by x minus 5. And then, it has been computed for all these values. So I have x and f and x for all of these values, which is 5 multiplied, it's almost 50. Okay. All right, so we want to use the solver to solve it. Okay, so this is, we're going to have only one decision variable, and that's x here, and there is no other. We only have one constraint, and that's that x has to be between 0.9 and between 5.1. That means that it has to be greater than 0.9. It has to be greater than 0.9 and less than 5.1. And there's no other actually constraints. And the objective function is the same. It has to be whatever the decision variable minus 1 multiplied by the decision variable minus 2 multiplied by the decision variable minus 3, and so on and so forth. So that's it. It's very, very, very simple, but it's actually a good example of showing you how your solver can get stuck into a local optimum, right? So we are actually maximizing, and the maximization should happen around 1.5, and it's about more than 3. It's like 3.3, almost 3.3. But this local optimum is about 1.5. Okay. If we start, say, by x equal to 3, we have to start with something. If we start with x equal to 3, the solver is going to stuck into this local optimum. Okay. So let me try. We are optimizing this f of x, maximizing actually. Our decision variable is going to be this one, and we have only one constraint, actually 2, and that's x has to be less than 5.1. Also, x has to be greater than 9. I've added those. I could have named this a little bit better. Okay. We are maximizing f of x by changing x, knowing that x is less than 5.1 and x greater than 0.9. Okay, we don't really need to check this because x is already greater than 0.9, so it's already kind of has been addressed here. And we're gonna select the GRG method to solve it, and I'm gonna click here to see what's gonna happen. So it says solver has converged to the current solution. All constraints are satisfied. It didn't say the optimal condition is satisfied here because it's not sure, right? Because we have actually optimal local optimal solution here. It actually found the optimal solution almost 1.49. No, it actually did not. X is 3.4454. So these are not actually correct values. 3.4 and 6. 3.54. It's almost here. That's 1.4. So f of x actually is 1.4. Yes. Okay. So yeah, it actually found this one. This is the local optimum that it has found. So it couldn't find this one. And if I try it again, it's going to be the same. Let me try with the different values, say 4. Yeah, it is stuck here. Right? Let me try with 2.5. Yeah, it goes back to here. But if I start from like kind of guided to not go to this one and go to this one, for example, I start from 1, say 1 here. Hopefully this time it's going to find the 1.36. So this time, because I kind of guided through this local, which is also global optimal solution, it didn't go to this one. So I guided it, right? And that means what actually we can actually conclude from this is, at least for the GRG here, and also for other algorithms, for this specific objective function, which is not convex or concave here, the initial solution would determine whether you would stuck or you would not get stuck into a local optimum. And we could actually have multiple local optimums. So it's could be very difficult to figure out whether you have the optimality condition satisfied one, right? So all in all, the point is your initial solution matters, and we cannot be sure whether most of the time whether we have the optimal solution or we have a local optimal solution. Any question? Let me close on this one too. And let's go back to, we were supposed to, I wanted to do actually a least square example as well. So let's do that. Okay, so this is an example for the least square, the regression model that I told you. So in regression, we have a bunch of x and y, or x and f of x, that we don't know what f of x is. So we want to kind of estimate what f of x is. Okay, so what we have is just data, and data is the x variable, or a bunch of x could be multiple dimension, x1, x2, x3, x4, and their y values, or their objective function, right? We don't know what the function is, but we have its values. And what we want to do is we want to estimate what that function is. And we want to find the best estimation using the least square method, which is kind of find a function which has the least error, okay? Least squared error. So we have a bunch of number here. For x equal to y, 1, the objective value is y, 1. For 3 is 7. For 5 is 8. For 8 is 10. Okay. And we're going to use the natural logarithm here. But it doesn't matter, because our objective function, the least square function, is a nonlinear function. So it's going to be a nonlinear optimization problem anyway. But here, just for giving you the idea that it doesn't have to be a linear function that you want to fit into your data, I'm going to try another function, which is the natural logarithm. So this is the function that we want to fit. A plus b multiplied by the natural logarithm of x. Okay. And what we are looking for, the natural logarithm of x is known. That's 2.7, almost 2.7 multiplied by x. Okay. So x is given here at 2.7, we know what it is. So 2.7 to the power of x. What we don't know, or our decision variable, is A and B. So this, we want to find the best parameters for A and B. Okay? So these are going to be our decision variables right now. These are just random numbers. That's why I said this decision variable. That's why I have used the pinky color, the red color here. So these are just random values I have given it. And now we are trying to model it as a least square function. Okay, so let's go ahead and do that. So this is how we would do it. The prediction is using the values that we have. I'm gonna do it twice. One for the best fit, which is of the optimal one, and one for just random start, which is 2 and 3 right now. I have started the best one also with 2 and 3, but it doesn't matter. So let's assume that we start with, it doesn't have to be 2 and 3. We can start with 2.5, whatever. So let's start with 2.5. And 3, let's say 6. Let's go and make it wide. So this is the predicted value, which is this actually function here. With A equal to 2.5 and B equal to 6. Okay, so this is what it means. And the function in Excel for natural logarithm is ln, as you can see here. So this is what it is. It says A, which is 2.0 right now, it's D5 plus B multiplied by ln of x. So B is D6 multiplied by ln of x here is A9. So that's going to give us the predicted value based on x equal to 1. I'm going to drag this down, so it's going to compute the function for different x's that we have here. And by the way, these are our actual y values that we want to fit the function into. Right. So we have plotted actually the Excel file, so it automatically, as you can see, it kind of plotted this to 4 points here, which is, as you can see, it's nonlinear. But you can see that is far from this point, so it's not a good fit. Okay, and we can change this by changing these values. Let me actually change it by back to 3. So it kind of fell down and it's closer to this. It's a better fit. And also, if I make it actually a little bit bigger, it could get better. Let me see here. 3.2 got better. 3.3 got better. 3.6. Very good. Right. So I'm going to start from these 2 points. Just the values. All right. So now let's continue with modeling. We need to find the least square value. That's going to be our objective function. So that's the error that we make for every prediction we have. Right now we have 4 predictions. This is 1 prediction when x is equal to 1. This is our second prediction when x is equal to 3, and 4, and third and 4. Right. So we have 4 prediction. We have 4 original or actual value. So we can find the error here. So the error is going to be the actual value minus the prediction. Okay, so it's equal to the actual value minus our prediction. I'm going to drag this down. That's going to be the errors for these. Okay, but these are not what we are looking for. What we are looking for is the sum of a squared. That's this is what it is. It's summation of error I squared, summarizing on all the I values. Okay. So actually, Excel has a function that does that for us. That's sum skew, sum squared. Okay. So I'm just going to grab all these 4 errors here, and it's going to square them and sum them up. So right now it's 2.63, but as you remember, I changed these values, so it's almost a good fit already. We cannot be sure whether it's optimal. We're going to solve it for optimality here later on. So let's go for the optimal one. So for the optimal one, we're going to write the objective function right now. So these are going to our decision variable. So we're going to do the same thing. This is going to be a plus b multiplied by, so it's going to be a, and I'm going to use the absolute value here. I could actually name this, so makes it easier to do that. Let me go ahead and do that. All right, okay, so now better. So this is going to be a plus b multiplied by ln the natural logarithm of x here, okay? 2.5, which is going to be the same as what we got here. So just copy it here. And the error is just going to be the original y values minus our prediction. If I change this, say, to 2 and 3, it's gonna change. And we're gonna use the sum squared here to square these values and then sum them up. So this is going to be our objective function. Let me use the calculation style for this, because this is going to be our objective function. Sum squared. I'm going to name also this one. All right. It looks like we have everything. We have, I'm going to also name x and y here. What else do we need? And that's it. So we have A, B, SSE, x and y. I could have named this just decision variable. Let's go to data solver, and then here is going to be our objective function, which is SSE. We are minimizing this by changing the values of A and B. And this is going to be decision variables. We don't really have any constraints here. So I'm just going to ask it to solve it. So it says solver has converged to the current solution. It didn't say optimal, right? So it's not sure whether it's optimal or not. But I have solved this before, and it's close to the optimal. It's actually the same. So it is optimal solution. And as you can see here, it even found a better fit than what we had before. Okay. So if I change this to these two values, you see that it is a better fit, right? Because this point right here is a little bit far away from this point. Okay, so we have a little bit of error here. So I'm gonna bend this value down, bend this curve down. So now the sum squared error is 1.14. This is the best fit, natural logarithm best fit that we have for these values. All right. Any question?
I have a question.
Yes.
On the model, the blue columns, what does the inputs, what does the X and Y represent in that column?
Yeah, this can be anything that you know define. For example, say X is your I don't know. X can be your number of customers, and Y can be your profit, whatever. Yeah, so Y has to be a function of X. We didn't define it, whatever X, Y here is. Yeah, that's actually, oh yeah, I forgot what it is. So this is actually for, if you remember, we had an advertising problem that we have, like the exposure to viewers. And back then we used actually a linear function. So the linear function was, if you show it, if you show the ad 1 time or 2 times or 3 times, the impact is going to be the same. That means that it's a linear function, the number of views on the impact of ad. But we know that for practical purposes, that's not true. If you watch an ad multiple times, it's not going to have the same impact on you every time. So it's going to have like a decreasing margin, a marginal effect. And that's a signal that the function of exposure should not be linear. It should be actually a nonlinear function. And that's what we do here, as you see here. So as you see, X is the number of times that we are exposing the viewers to the ad, but the impact, which is the unit sold, the impact of advertising, is not linearly, is going to add up. It's going to curve down, right? The impact is going to diminish, right? So that's what it is. But it can be for any other problem as well.
And so what we were asking was that given those X and Y inputs, the objective function was like just chosen for the sake of this problem, but essentially you could use this to do any function using X and Y.
Yeah. So you just have to have, that Y, whatever your problem is, you know that there is something that is depend on something else. Okay. So in this case, this is the impact of the advertising, which is selling a product, for example, right? Selling a product. And that in advertising has an impact. So you want to see how, what's the relationship between the number of sales and the number of times that the advertising is being actually exposed to people, the viewers, right? So you have gathered kind of a data for this, for the past histories. Say, in 1 week, you show the ad, say in one region, say twice. In another region, in 1 week you showed it 4 times, 8 times, whatever. And then based on your sale values, so you have gathered those data both for the number of exposure and the number of sales. So you kind of have both X values and Y values, but what you don't know is the relationship between Y and X. You know that it's kind of related, they are related, but you don't know what the mathematical function is, right? In the past, when we first time actually we solved this problem, we assumed that it's linear, which doesn't make sense. It's not linear. If you see an ad multiple times, it's not going to have the same impact on you. So here we assume that it's not linear, and I went with a nonlinear function, which is a natural logarithm. And I assumed that is a natural logarithm, but I didn't know what A and B, the parameters are here, which is like the starting point and kind of the slope, right? So here, I found that A and B, the best values for those A and B based on the data that I have, right? So I kind of had a template function. I assumed that it is natural logarithm, but I didn't know, how should I bend it, and what should be the starting point. And I used the best fit model, which is the least square function here, based on the data. And using the optimization here, I found A and B. So A and B was our decision variable. These A and B were our decision variable. X and Y were our data. It was input. And the least square function, which is the summation of error, was our objective function. Right, so this is going to be our best fit. So right now it says A is 1.37 and B is 4.28, and this is how it almost looks. And this is how we estimate it. So we estimate. We still don't know. There could be a better function that fits this, but this is based on my assumption that it is actually natural.
Okay, yeah, that helps. I was just struggling to understand like the bigger picture of why we're doing it.
Yeah.
So just sorry if you answered it, it's still a little lost on me. So now that we know A and B, how do we apply that? Or like, how is that helpful to us?
Well, now you know that, okay, if you want to, you have the Y function, that's how many sales you want to have, then you have of course, you're going to have a budget for how many times you want to advertise, right? So that's based on your optimal Y values or your goal for how many sales you want to have and your budget. Then you're going to, using this formula, you can figure out how many times you have to run the ad. This is what it tells you.
Gotcha. So now that you have the rest of the formula, now you can work backwards from your desired target to figure it out. Okay. Thank you so much.
Yeah, because I found the A and B, the optimal A and B, and also X is going to be your input. So that's your decision. And that's meaning, okay, how many times you want to run the ad? What is your goal? Your goal is going to be, okay, how many sales you want to have based on how many you have to run it, and what's going to be your budget for the advertising.
Okay, yeah, thank you. That all came together. I appreciate that.
Sure. All right. Let me go to, all right, so we are actually done with the first part of the lecture. We have 3 examples kind of here. Let me open up the next part of the lecture, part 2. I'm going to close all the Excel file that I have and open up the next one. So we're gonna get the pricing. All right, so part 2. We're gonna solve here. We're gonna solve a financial example, which is also going to be a nonlinear programming example. Since I have installed the add installer table, you have not also experience them. Whenever I want to open an Excel file, is going to be search. All right. So now let's go another example. So before I do that, I want to talk about the convex and concave kind of thing that I mentioned. So generally, we are not sure whether using the GRH or other methods in solving a nonlinear programming model, whether we have found the optimal solution or we are stuck in a local optimal solution. There are certain scenarios that I said that we can be sure. And that's actually when you have a convex function and you are minimizing convex function, or you are maximizing a concave function. Okay? So a concave is any line connecting 2 points on the curve that lies below the curve. That means the slope never increases. Okay, so it's kind of going down. Right? So if it's always going down, for that, you can be sure that you'll find the optimal solution. Or if you are minimizing, it has to not be increasing. So it has to kind of go up or stay the same. That's going to be a convex function. That's a convex function. Yeah, something like this. Okay, so this is like a convex function. As you see here, it's not increasing, right? It's not increasing. So minimization, this function is easy because we can be sure, actually it's not easy. We can be sure that whether we have found optimal solution or not, because it cannot have a local optimum because it's non-increasing. Okay, so it cannot have a local optimum. Also true for the concave function. So where the concave function is decreasing or non-increasing, as you say. So we cannot get stuck into any local optimum because there is no local optimum. So the solution that you find, the optimal solution that you find is actually optimal. Example of this is, for example, when 9 minus x2 is, this is a concave function. So maximizing this is maximizing the natural logarithm is also natural logarithm is also concave. Actually, the usual logarithm also is concave as well. So maximizing that is can be ensured you have found an optimal solution. Example of minimizing a convex function, x2, that's a convex function, and y equal to e power of x. That's also or 2 power x or 3 power x. That's also a convex function. So minimizing that, you can be sure that you're not stuck with a local optimal. And if you actually run these problems in Excel, it's going to give you the message that the optimality conditions are met. Okay, it's not going to say that the current solution is found. But when it says the current solution is found, it means that it's not sure whether it is the optimal, the global optimal, or it is stuck to a local optimal. So what if these conditions don't hold? Then we are not sure. We are not sure whether we are in a local optimal or we are in global optimal. So that's unfortunate. And that's most of the cases, right? So the overall the case, there are very small scenarios, number of scenarios that you have a concave function that you are maximizing, or you have a convex function that you are minimizing. Most of the time it's not convex, no. So these conditions are not true, are not holding true, so you cannot be sure. So what should you do if you are stuck with whether these conditions hold true? There are certain things that you can do. You can actually try different initial points. As I said, the initial points are important. So you can actually run it multiple times with different initial values. And another actually a good option that you have with Excel solver is you can ask it to simultaneously run it with different values, with different initial values. So that's called actually population. So it has, you can actually give it the numbers. Say, I want you to run 100 models with different initial points, and then give me the best answer. So that's actually good, right? That's a good approach too. Okay. But it's gonna increase the runtime of your model. So let's see the financial example, which is also nonlinear. Many businesses try to set their product prices in a way that maximizes revenue, right? So as a manager, you would want to price your product in such a way that your revenue is maximized. But your revenue depends on demand, and the demand also depends on prices, right? So revenue is a function of both the demand and the price, but also the demand is a function of price. And when the demand is higher, when the price is higher, of course, you're going to get a better, more revenue, but also your demand might actually decrease, because when a product is more expensive, less people are going to buy, right? So there's this kind of a nonlinear curve into this problem. So that's better. That's actually a good signal for us to model this problem as a nonlinear function rather than a linear function. There is a whole subfield of analytics called the revenue management, which around this idea. So the simple function is price multiplied by demand. That's your revenue, right? Price multiplied by demand, PD. But the demand is also a function of P, right? So demand itself is a function of price. We say we don't know what it is, say F of P. So revenue would be price multiplied by F of price, okay? Or revenue is equal to P multiplied by F of P. F of P is the demand, which is going to be a nonlinear function, right? This is nonlinear. F of P is a function of P, which is multiplied by P. So revenue is nonlinear. So this problem is going to be nonlinear. So what we want to do, we want to find P as a decision variable. We want to find the best, the optimal pricing such that our revenue maximized or our profit maximized if we have also the cost, which also is kind of depend on our demand, right? But that's our goal. The goal is to maximize the profit. Suppose a product that costs $3.25 to make has been sold at various prices. We have the list here for 4 different prices. When the price was $10.99, the number of sold was 40. When the price we decreased the price to $8.95, and the demand kind of increased to 53. We decreased it a little more to $7.49, and our demand increased, and our number of sold also increased, and we again dropped it to 5.99, and we get more demand, so we sell more. Right, so as you see here, our demand has increased by dropping the prices. So from these data, we can estimate how sensitive demand is to price, and what we are looking for is what should be priced. These are just 4 values here, but we want to see, okay, what should be what is the optimal pricing here, so that our profit is maximized, knowing that the profit, which is a function of revenue and cost, is a function of price and the demand, and also the demand is a function of price, right? So knowing that, we want to find the best pricing. If we want to go back to our influence chart, this is how it will look like. We start with the output, which is going to be profit. We want to maximize the profit, and what goes to profit, the total revenue and the total cost, right? With the profit actually is equal to total revenue minus the total cost. What goes to total revenue? Demand and price. So demand and price. But demand also is a function of price, and also based on historical data that we have, that's going to be our input to determine the demand. And total cost also is a function of demand and the unit cost, or cost per unit for the items that you want to sell. All right, so what we want to do, we want to find the best pricing. So we assume that demand is a function of price, F of P. So we're going to go into 2 cases, consider 2 cases. One case, we assume that F of P, the function of price for demand, is actually linear. So we assume that we're going to go with this. Is linear, is A minus B multiplied by P. So B is a slope here. And we assume that B is positive. So here, each $1 increase in price, it's going to reduce the demand by a factor of B. Okay. And the next case, second case, we're gonna consider a nonlinear function for demand and price. And we're gonna use what is called as the constant elasticity. So D, we assume, is equal to the parameter A, which is on a slope, multiplied by P to the power of B, where B is negative. So that means that it's kind of A divided by P to the power of B. Okay. So in this formula, in this case, each $1, each 1% price increase, it would actually lead to the demand to be reduced by B price, or the absolute value of the percent. It's going to drop. The objective is to maximize the profit, so which is going to be total revenue minus total cost. So let's do that. Let's model this problem using just these few data that we have in Excel. So there is an example for both the data and the done version that I have uploaded on Excel. I'm going to share this with you. Okay. Let me save this. I want to move this. I see. So this is already prepared, so you don't have to do all the work. We have 2 cases, as I said. One is f of x is linear, a minus b multiplied by price, and the other one is a multiplied by price to the power of b. B is actually a negative value, so it's going to be a divided by p to the power of b. Okay, so these are the data that we have. The prices here, these are actually should be dollar values, and the number of demands on the second column. Okay. And we also had the cost per unit for our problem. And that was $3.25. That's unit cost. So in this formula, in this case, we assume that the function, the demand is a function of price, is actually linear and is equal to A plus B multiplied by P. Okay, and B actually is a negative value, because the demand has to decrease when price increases. So they need to have a negative relationship. A here is the intercept and B is the slope. So you want to find A actually and B. So we can start with different values here. The price is going to be our decision variable. We want to set the price, and the profit is going to be our objective function. That's why we use the gray color for that. All right, so let's go ahead and start with this. Okay, so how we find A and B here? If we assume that the relationship between demand and price is linear, there is actually, we can actually run this. I can actually ask Excel trend line. So this is a trend line, and I can act to linear. So this is the linear estimation based on this, okay? But it can also give us, should be able to give us the display equation on chart. All right, great. So it already gives us A and B. This is A, 156.54, and this is B, negative 11.076. So this is based on the data. This is our estimation of the function. We have the function. But if you want to do it another way, actually Excel has a slope and the intercept function that we can find based on the data, the input data. So the intercept is just intercept. So A can be found using the intercept formula. And it gets two parameters or two inputs here. The known Y values, which here is going to be our demand. So I'm going to click the demand first here, grab all the demands here. And the next parameter that are known X's, or which is here are prices. So I'm going to select those later. And the second, I hit enter, as you get 156.54, which is the same as I found here. Okay? And for the slope is just a slope. Again, it's going to get two inputs. The first is the Y variables, Y data, which is the demand here, comma, the price. Second, it gets the negative 11.8, which is the same as this. If I give it another decimal point, it's going to give us all the points that we have. So we have the intercept. We actually have the function. This is the function for demand based on our assumption that this is linear. Now the price is going to be, here is going to be our decision variable. Now that I have the assume for any price that we have here, D is going to be a function of price, and that's going to be A plus B multiplied by price. Okay. So right now price is 0. That's why the demand is 150. So if I go with, let's say, 5, it's going to drop, right? So by changing the decision variable, which is price here, our demand is going to be changed because demand is a function of price. Next, we have the total revenue. We are going to compute the total revenue and total cost to get to the optimal, the final output, which is the total profit here. Okay. So to do that, we need to have revenue and cost. What is how we can get the total revenue? The total revenue is equal to demand multiplied by price. So this is going to be demand multiplied by price. And the total cost is going to be demand multiplied by the unit price. And total profit is just the revenue minus the cost. which is 22. So right now, we don't have any profits. So I have to go with different values, but it doesn't matter. So as you see here, it's not very easy. All right, got to positive finally. And it looks like that's about it. So I'm going to name some of these numbers here. This is going to be our objective function. This is going to be our decision variable. What else do we need? Decision variable. I think that's it. We actually want to all right. So let's go ahead. Data solver, and we want to maximize the profit by changing the price, which is a linear function. We really don't have any constraint here. But here, let me solve it first, and then we can get a negative price here. So I'm going to check this, make sure that this is checked. I'm going to get this solved. Let's see what we get. So right now it's 6. Oh, yeah. It blew out of proportion. Just increased it. So we need to make sure that we need to set a limit on price. Otherwise, it's just gonna increase the price infinitely. So I'm gonna say that okay, the price cannot be greater than 12, for example. Or 15, say. 16. Positive. So we need to put actually a limit on the price, otherwise it's gonna go. All right, so I'm gonna say the price should be less than 15. Price. We assume that this is another input. We want this to be less than 15. Okay, let me go back to the solver again. I'm going to add a constraint here. And that is the price should be less than equal to 15. So it found a solution. It is exactly 15, but we are not sure whether this is actually optimal or not. So we can try the options that I mentioned. So I'm going to get to GRG nonlinear. So here we can say start with multiple lists. When I say I don't want to go with 100, I'm going to go with 10. I'm going to see 2. And let's run it. All right, it got to the same. So I'm going to increase this when we come back after the break. We're going to increase it to see if we can actually get this fixed to get a better solution. The solution should be more than 6. The profit should be more than actually $6. Okay. So let me All right, let's go back to our lecture. So in the break, I had the time to go over my computation, and I figured what was wrong. Share this screen. So apparently, the revenue is computed wrong, and instead of multiplying price by demand, I have used, because they are next to each other, my keyboard. So it has to be multiplied. And let me also check the total cost. Okay, that seems correct. And the profit is, maybe it's a good thing to name this. Should I already name? I already name the price, and the price. I'm gonna also name the total cost. So now I'm gonna say demand is equal to intercepts. I'm gonna also name these. So demand is equal to the intercept plus B multiplied by price. So that's better, that looks better. Intercept plus P. So this way it's easier to track if you have made a mistake or not. I'm going to also change this and use demand and price name that I have used. So price multiplied by demand. Okay, total cost, that's equal to unit cost. I hope I have named this. Check what I'm going to also name it. All right, now total cost is going to be unit cost multiplied by the demand. And the profit is just going to be revenue minus total cost. Change this. All right, now let's go back. So I want the price to be less than 15. I think right now it should be fine. So even if I don't put the less than equal to the price equal to less than equal to 15, that should work. Price limit going to also like this up here in my model. Somewhere. Okay, good. All right. Let me not use this. I want to see whether it can solve it. So let's go ahead and solve this. It says solver has converged to the current solution. It didn't say optimality condition are satisfied or not. It says all constraints are satisfied. That means that your solution is feasible. So that's a good thing. And the optimal price here is 8.69. And the total profit is 327. And this is the same thing that I got before. So this is actually the optimal solution. Okay. Any question over here? No? All right. So let's do case 2. So in case 2, we assume that the relationship between demand and price is not linear that I have here. Is actually non-linear, as I mentioned before, and it's A and a slope multiplied by price to the power of P, power of B. So I want to find A and B here. So what I can do is I can click on one of these points here, right click on it, and then ask for add trend line. And it has a couple of options here, as you see, but I'm gonna go with the exponential. (259) e to the power of, okay, so I want to go with power actually. 1277 -1.4045. Yeah. Okay. So this is our A and B. We didn't have to do any computation. So A is 1277.2 and B is negative 1.453. Okay. Did anyone get how I did come up with these values?
Do you mind repeating the trend line steps you took?
Sure.
Thank you so much, Professor.
I'm gonna go back. Okay. So let me get rid of this line. You click on these points and then right click, and it's gonna get you this option of add trend line. If you click on it, it's gonna give you this option here that you have multiple functions. You can go with exponential, linear, which is the default, logarithmic, polynomial, power, and moving average. So what we are looking for is P to the power of B. So we have to go with power here. So I'm going to click on power, and then I'm also going to ask it to display the equation on chart. And we can also ask to show the R-squared values, which is for our equation. So this is how it did it. It actually fit this line here for us. And it also shows us the equation. Okay.
Thank you so much, Professor. I figured out what I did wrong.
So A is 1277.2 and B is negative 1.453. All right. So now we have the function. This is the function. Demand is equal to A multiplied by price to the power of negative 1.45. Okay. So now we have we can actually write the demand function based on price. The price is going to be our decision variable, and the demand is going to be a function of this price, which is, let me again go ahead and name this here. So the demand is going to be A multiplied by price to the power of B. What does it say? Our price is 0, that's why it's good. I'm gonna go with 1. Total revenue. So total revenue is demand multiplied by the price. And total cost is demand multiplied by unit cost. This is unit cost. And profit is just the revenue minus the cost. Okay. So now we have demand, a function of the price. We have profit, a function of demand and a function of price. We want to set the best pricing. That means that we want to find the optimal price so that our profit would be maximized, assuming that this is the relationship between demand and our price. So I'm going to go to the data solver and I'm going to ask it to optimize the profit by changing pricing. And let me not add any constraint right now. So let's see if it can solve. But yeah, it actually found just the optimal solution. So this is a as you can see here, this is a non-increasing function, right? So this is like a concave, right? This is a concave function, and this is actually for the debate between demand and price, not for the total profit, but we are maximizing the total profit, and total profit is actually a function of price and demand, and demand is a function of price, which is nonlinear, but overall, I think it's going to be concave. Okay, so the total profit is a concave function of price and demand. So we can actually rely on that theorem that the solution that we found is optimal, but we can be sure that it's not local optimal, it's actually global optimal, okay? Because it's concave. As you can see, it's concave. Non-increasing. All right, so our optimal price is 10.42, and with that we can actually our demand is just going to be 42, or we can round it up to 43, and we're going to make a profit of almost $4. Okay. All right, so this is a type of problems that it was really easy. It was very simple. But as you can see here, the concept is that we have a nonlinear function, objective function, or we have nonlinear constraints, or even a part of even the objective function or the constraint, if that part is, if there is only one part that violates the linearity of the model, that's going to make the model non-linear, and we won't be able to solve it using simplex algorithm. So we have to use nonlinear solver. And as I said, generally, nonlinear programming are more difficult to solve, and most of the time we are not sure whether the solution that we have found is optimal locally or global optimal. That kind of not good news, right? Any question? Don't say. Close this. Let's go back to our lecture slides. All right. So the second function, it was what is called as elasticity, based on elasticity demand, and that means that, okay, so we can actually think of items, whether they are elastic or not, the demand for them, and they generally, those items that are not essential, that means they are kind of luxury, they can be delayed, they are not required right away, you don't need them, you're not going to die without them, and they have substitutes, or they may or may not have substitutes. Those can be overall thought as elastic demand. It means that if you change the price for a percentage, the demand is going to change based on a percentage of price, or function of price. So, but we have also items that are not elastics, you can say inelastic demands. So items that are necessary, they are not luxury, they are essential, they need it right now, and they don't have any, they are unique, they don't have substitutes. For example, Pepsi is not needed. I don't think you would need Pepsi, and it has actually substitute, and you don't really need it right away. I hope so, and it can be delayed. So for Pepsi, for example, if the price increases, the demand is going to go down by a percentage, And you may at some point you may actually switch to Coke or other sodas, or just go with water. Okay, and that's about it. That's what we want. So talk about for the finance problem. So let me go to the next example. Open up the third one, the third part. All right, so this is the third part. By the way, this is the 7th chapter in the textbook. So we're gonna go another type of problem that can solve is similar to the shortest path kind of concept, but is we're not looking for the shortest path, we are looking for the safest path. Okay, so we are dealing with probabilities here. So our function is not our model is not going to be linear. Suppose that we have a trucking company and they are specialized in transporting hazardous material. So what matters for them is not transporting them with the shortest path at the fastest time, but what matters is to transport them at the safest possibility. That means that the safest, the safest path, so that they won't have any accidents. So there won't be any spill and any danger, right? So what we are looking for in a network of roads and cities from origin to destination is not the shortest path or the fastest path, is the safest path, given that we have the data for any path or any road from one city to another, how safe that road is. Based on historical data. Suppose that we can say based on historical data that 99% of vehicles from past 10 years they haven't had an accident in this road or any other way. So with the historical data we can estimate kind of those probabilities. So based on those we are looking for the values on our network of roads between cities are not going to be the time from getting from A to B or the length or the mileage between two cities. They're going to be the probability of how safe or how unsafe they are. Okay, and this problem is called the safest path, and it's actually nonlinear. So the goal is to find the path with starting from the starting point. We are assuming our data we're starting from LA and we're going to go to Texas. Amarillo, Texas, and we want to minimize the probability of accident, or we want to maximize the probability of no accident. Either way, it works. They're the same. You have the data, the probability of the roads, accident or no accident, and our decision variable is for all of these roads in this network of roads between these cities, whether we would include those edges or arrows or arcs or roads in our path or not. Okay, so it's going to be a 0-1 binary decision variable, and we're going to have formulas as a flow inflow outflow kind of thing, that the same thing that we did for shortest path or fastest path. So this is not exactly the general network, but it's kind of showing part of it. We are starting from LA. You see that from LA we can go to the 3 neighbor cities. We can go to Las Vegas, we can go to Phoenix, we can go to San Diego, and the values that you see on these edges are actually the probability of accident. So for example, from LA to Las Vegas there is a 0.0003, or there is actually 0.03% probability that you're going to get into an accident. For LA to Phoenix, that's 0.02, and for San Diego is 0.004. So between these 3, it looks like LA to Phoenix is better, and so on and so forth. So we're going to go, which way should we actually pick, and we're going to go to destination, which is shown by the red color here. So our decision again is for all of these edges, these are going to our decision variable. Okay, so LA to Las Vegas, if if X LA to Las Vegas is equal to 0, that means that we're not gonna pass from LA to Las Vegas. That's not going to be part of our path. If it's 1, that means, okay, we choose to go from, it's part of our path, we choose to go from LA to Las Vegas, and then we have to continue from Las Vegas to somewhere else. Okay, so let's actually go ahead and open up the Excel file for that. Okay, let me part of the all right. So let me actually give you more explanation before we end up into Excel and modeling. So we're going to have a data origin destination similar to what we had for the shortest path or the fastest path, except that we're going to have the probability of accidents on the arcs as a value, and not the mileage, or not the how long it's going to take. Okay, and probability of accidents. We're going to have also required outflows. The decision variable is going to be flow for every pass, or for every road, and between every 2 cities that are neighbor. And the key calculated quantities are the probability of no accidents is equal to 1 minus the probability of accidents multiplied by flow. So flow can be 0 or 1. If it's 0, that means that we're not going to actually pass that road. So the probability of having an accident is 0. Is that the probability of not having an accident is 1, or the probability of having an accident is 0. So you either have to go with minimizing the probability of accident or maximizing the probability of no accident. If you choose, you won't be confused here. So let's go with the probability of no accident. Okay, so we're going to maximize the probability of having no accidents, and that's going to be 1 multiplied by 1 minus the probability of accident, which are the values on each road between 2 cities, multiplied by whether the road is in our decision pass or not. And you also need to have the, if you remember, the outflow and inflow constraints that we have for the shortest path. So it's going to be similar. So we're going to have the net outflow for each city. For origin, the net outflow should be 1, and for the destination, which is Amarillo, Texas, it has to be -1. For any city in between, the net outflow should be 0. For that, in Excel, we're going to use the sum if as we did for the shortest path, if you remember. So sum if is going to take, we're going to give it 3 parameters. First, the origin of cities, the list of origin cities, and then the city that we are interested in for outflow for this specific. So we can actually drag it down. I'm going to show you in a bit in Excel. And then the flow variable, whether that city is going to be, whether that road is going to be part of our path or not. Minus, this is going to be the outflow, minus the inflow. So for the inflow, we're going to sum if on the destination side list, and then the city, and then whether the flow is or not. So that's going to give you the outflow minus the inflow, which is the net outflow. And that has to be 0 for the in between cities, and it has to be 1 for the origin, which is Los Angeles, and it has to be -1 for the destination, which is Amarillo in Texas. All right, and that's about it. So we also have to make sure that the net outflow constraints are met, and also we have to input the constraints that the flow variables are binary, and that's all. That's all we have. Let me open up the Excel file here, and I'm going to share it with you. And I'm going to save it as something else, so I didn't lose the original file. one. Put it in a folder that I can delete it later, so I wouldn't get a lot of unwanted finds on my computer. All right, so these are the data that we have: the origin cities, the destinations, the probability of accidents here. And I have made the origin cities in a different color, which is blue, Los Angeles blue, and the destination, which is Amarillo, as another color, the different color red here. And these are the, we're gonna have the node balance constraints within for all of these cities, as you can see here. And then we have to write the objective function and probability of no accident. We have to compute that as well, and then build up our model, right? So let's go ahead and get started with all of that. So we said that we want to maximize the probability of having no accident, and these are actually the probability of having an accident. So we need to find the probability of not having an accident. Okay? So the probability of no accident. And that's just going to be 1 minus these values. So I'm just going to drag this down, and it's going to be our values here. Let me actually go ahead, and before I do that, I'm going to name these. Not left, upload, and I actually want this to get rid of this, and I'm going to move this here so I can put the decision variable, which is our flow here. So flow here, and this is going to be our decision variable, and this is going to be binary, whether 0 and 1. And these are going to be the probability of no accidents. So the probability of no accidents is going to be 1 minus these values, whether they are. So that's going to be 1 minus flow multiplied by the probability. One minus whether this is selected or not, multiplied by the probability. So because it's not selected, the probability of having an accident is 0. This is actually the probability of not having an accident is 1. Okay? I'm going to drag this down here, and of course, all of them are going to be 1. But if I choose any of these passes, the probability, as you see here, is going to change. This is what I'm doing. And did I get the flow? I get the flow, but I didn't get the. So name this. Okay. So what else do we need? We need the constraints for the node balance constraints, the net outflow constraints here. So I'm going to compute the net outflow here. Net outflow. And the net outflow. And I'm going to use sum if the range. I'm going to go with origin first, and then the criteria, which is this city, and then whether it is 0 or 1, the flow. So it says flow, origin, G5, the city, and the flow. So what this does is actually going to say, find whether for this city that we are in this row, right now we are in this row, which is we are in Los Angeles. Okay? For Los Angeles, go over on the origin list and find the row that Los Angeles is in the origin, which is like these three, and then go to the flow list and find whether that Los Angeles flow has been selected or not. That means, okay, if the flow is 1, right, sum those up. Okay. So right now, because Los Angeles is not none of these actually are selected, so that's why it's actually 0. Right? So that's actually the outflow. I want to also do that for the inflow. That means that instead of Los Angeles to be an origin, I want it to be destination. So I want to get all of these flows that comes into Los Angeles. Okay, so I'm going to go with sum if again. I'm gonna this time I'm going to move to the list of destination city when Los Angeles is destination city, and again whether Los Angeles has been selected or not into our path. Okay, so this is the outflow from Los Angeles, from this city, minus the inflow to Los Angeles. This is going to give us the net outflow. Okay, and if I drag this down, it's going to compute it automatically for the rows here. Okay, so this is not actually a feasible solution, as you see here, because the net outflow for all cities has to be 0 except for the origin, which has to be 1, and destination, which has to be negative. Okay, so I'm going to write the required row here. So this is going to be our actually input kind of, and for origin is going to be 1. For others has to be 0, and for the destination has to be negative 1. So these are our input. I'm going to use the input color to color it. Okay, and the net outflow should be exactly equal to this. So this is, I'm going to use equality sign here. This is just for model presentation. It doesn't really matter. Just over communicating between you and the model, and also if you give this model to someone else, he or she would understand it. It doesn't really matter. Like the solver, it doesn't require this, right? So this is just for clear model building and communication. Okay, so we have the net flow constraint. We need to come up with the objective function. What is the objective function? The objective. So I'm going to write the objective here. This is going to be bold, and the objective actually is the probability of no accident. Okay, probability of no accident, and that's actually equal to. So this is what we have to do. We have to sum we have to actually multiply these by each other. Okay, so if you multiply every cell in this column together to get the probability of no accidents, right? And Excel actually has a function for that, and that's product. So product, I'm going to select all of these values, and it's going to multiply these together and produce the result for us. So this is our objective. I'm going to use my output style here. This is what we want to maximize. Okay. So we have our objective. We have the net flow constraints, and we have the decision variables, and everything looks fine. So it looks like we are almost done. We can go to the solver. Let me actually, while I'm here, I'm going to add this into formula, into name these. Okay. Oh, is that one? Oh yeah, this is this one. Probability of and did I name the required? I didn't really name that one. origin, flow, destination, required method flow. I don't have the method flow required. I'm going to flow and required. I'm going to also name this. Okay, so I think I'm done. I'm going to go to solver. I'm going to ask it to maximize this by changing the flow variable and adding the constraints. I want the outflows to be equal to the required and also I want the flow variables to be binary, BIN add. Okay, so it says maximizing the probability of no accident by changing the flow decisions. The constraint is the flow has to be binary and the net outflow it has to be equal to the required. So all right, so we're gonna pick the GRG nonlinear solver or method. This doesn't matter really because it is binary. So binary is 0 or 1, so it's already positive. And I'm gonna say I want it to 0 optimality. I don't think I need to mount a list now. I think we can find it pretty fast. Let me try it. So right now, if you look here, even the solution is not actually feasible. The solution is not feasible. So let me try it. It says the solver found a solution. All constraints and optimality conditions actually are satisfied. So it says it actually found the optimal solution. And it says, all right, it says go to, from LA, go to Phoenix, and then from Phoenix, go to Flagstaff, and then from Flagstaff, go to Albuquerque, and then from Albuquerque, go to Amarillo. And for that, the probability of no accident is 99%. I'm going to change this to percentage. And the required condition minimum flow is also satisfied. So, good. Any question? Okay, let me go back to our lecture slide. All right. Just 4 out of 8 fatal arcs actually that have flow of 1. That means that we only have visited 4 cities. For our final pass at 4 roads. The safest pass was from LA to Phoenix, from Phoenix to Flagstaff, and then to Albuquerque, and then the destination. The overall probability of having no accident was 99%. 99.0001. What if the so we can do some sensitivity analysis that we used to have for other problems. So let's do it for one of the cities that we are visiting in the middle, and then we trying to change the probability of having an accident or not having an accident, and see how much that would actually impact our flow or our safest path, optimal solution, optimal safest path. What if the Flagstaff to Albuquerque, that road, get more dangerous due to bad weather? For example, we wanna say how would that change if we increase the probability of having no accident from 0.001 to 0.005 by an increment of 0.001. So let's do that. I'm gonna go back to Excel. That was Flagstaff to Albuquerque. So I'm going to open up the solver table. Because we're going to do analysis here. Yes, we have. Right. Input cell. So we want to change the probability of having an accident for Flagstaff to Phoenix. Flagstaff to Phoenix to Flagstaff. Was it Phoenix to Flagstaff? It was Flagstaff to Albuquerque. Flagstaff to Albuquerque. This one. So we want to change this. Flagstaff, Albuquerque, probability accident. What a long name. Can I start from 0.01, which is right now. Flagstaff to Albuquerque. Okay. And I want to increase it to how many? 5.05? 0.05, an increment of 1.01. And I want to see the impact on the flow, which is our optimal, our safest path. And so the probability of no accident. So it's gonna, I think, take a little while to compute. Can actually see the computation that it does here. Check itself. 99%, 99%. Try a solution. Still running. This one will take about a minute. Nope, it's more than a minute. For your case, it could be different. It depends on your computer, of course. The faster and having more RAM, I think, would help. Not really RAM would help here. I don't think very much RAM. But if it would if you're running multiple programs as I have here, running a lot of stuff here. So that could impact it. So problem 5. I think this is the last one. Yeah, that's the last one. So it should, when it solved this, it should have stopped. And this was a pretty simple problem with not a lot of constraints or number of variables. So imagine if you have a larger realistic problem, how long that will like. That was in command, so it's still running because it's a binary nonlinear programming, so it's more difficult. No, I can't help it, so I have to just wait. Okay.
Professor, can I ask a question while this runs?
Sure.
I was wondering about for the next assignment, what is the best way for us to make the project proposal? Is it just like a description in a Word, or do you want like an outline of it as an Excel doc?
Well, the description has to be there. Otherwise, if you just put the model, I wouldn't understand what it is, right? And you don't really need like have a data or like even Excel file. No, you don't really need an Excel file. Just a description on a PDF, a Word that has been converted to PDF or whatever. A PDF file that explain the problem. So it's like a proposal. You don't have to go like into detail. What's your the detail of the model.
Thank you so much.
Well, I didn't expect it to be taking this much. Oh, okay, great. Finally. All right, so these are the flag stuff. As you see, the probability of having an accident here, I'm going to make it a little bit more readable, a little easier. And you can see here, we can't really make sense of any of these values here. So I'm going to select these origins and put them here in the diagonal. I'm going to insert the row here and copy the destination. I'm going back here. I'm going to put it back here. So why did it do it? Search. So copy, paste. Okay. Okay. So now I want this to this way. Smaller. Format alignment. Okay, now it's better. So this is Los Angeles to Las Vegas. This is back to center them. So I'm going to center these values. Okay, so this is much better. All right, so let's see. The output values. Value 1. So go to the probability. The probability of having no accidents. So as you can see here, by increasing the probability of having an accident, the probability of not having an accident increased for our surface pass until actually at a point where the flag stopped to flag stopped to Albuquerque. When the flag stopped to Albuquerque, at this point, when it got to when the probability of having accidents increased to 0.03, it actually became unsafe. So our safest pass dropped that road from our safest pass and included another road, so that from now on it wouldn't matter to the probability of having no accidents if you increase the probability of having accidents for the Flagstaff to Albuquerque, because it is now no longer in our safest pass. Okay, so it actually has changed here, and you can see it from here. If you find the Flagstaff to Albuquerque, this is so for the first two, it's in our actually our path, and when it got to 0.033, it was dropped, so it is no longer in our path. Actually, what is in our path is Tucson to La Crosse and the Phoenix to Tucson. So the Phoenix actually to Tucson, so it became part of our path. And this is the kind of analysis that you can do. You can actually do it on other parameters or other inputs as well. Any question? Okay. All right. No question. All right. Thank you very much. Appreciate everyone.